Hello, everyone. My name is Alex Mavridge, and I'm going to be presenting you the use of functional and generative components for custom OpenBridge substructure elements. Right? So what is a functional component? When to use it? How to use it? How to create one? Right? So just in a nutshell, I can say that a functional component is a parametric cell that becomes part of the bridge. So this parametric cell, again, a microstation parametric cell, it's just a functional part of the bridge. And that's how we use it in OBM. Now, you know that we use our piers, in that case, for example, or abutments, we use it as we want from the dialog boxes, right? So we have parametrics there, we can modify it quickly. But there will be cases in which the special structure that we want, it's not quite right inside the libraries that we offer. Even though they're extensive, sometimes it's not exactly what we need. So we need something custom. And one way to get customized is through a functional component or a parametric cell. So that is what we can say is the design intent. So how we achieve these parametrics, how we make it behave, right? If you study the creation of microstation, again, parametric cells, in which also there is extensive material on how to create them, it just works on the use of constraints in 2D and in 3D. Constraints like you see on my screen, that this element has to remain parallel to the other one, or this element needs to be perpendicular to another one, and so on and so forth. But then this will be just, let's call it hard-coded constraints, right? Parallel, perpendicular, fixed locations in 2D and in 3D, as I said. But the power of that parametric cell is that these definitions, as well as the dimensions, could be made into variables. So that constraints, right, and the behavior of that, and dimensions in general, angles on that, could be assigned certain variables. You customize the name, and then your cell will be parametric. So you will be changing, for example, a variable called footing length, cap height, something like that. So again, for the user will be just very much straightforward. So this will be the creation of the parametric cell. Now, how it knows that it belongs to the bridge? One thing is that we tag it. So every element that we create, we tag it, and then the software will understand that the solid that we are highlighting, it's an abutment, it's a column, it's a cap, it's a footing. And we're doing that because then as these solid elements come to life into our bridge, then it could be used to compute quantities. So then we know what element is what, right? So that is the next step. Also, we have included the option to variable mapping. What is that, right? You know, for example, that when you place a cap, right, in the dialog box, you can say adjust the cap according to the deck width, and it will do it automatically, right? But then when you do a parametric cell, it doesn't know that. So the next step on defining, for example, if we go into the workflow, the first step is defining the constraints. The second is assign that constraints to variables, tag the solids created to what element of the bridge they belong, and also the last step will be the OBM variables that we expose. We don't expose all of them. So far, this is what we have. We say the variable that I customize it in my parametric cell, length of cap, for example, right? It corresponds to an OBM variable that is cap length. So that's the variable mapping that we use. So how you create a parametric cell, right? So here we have, this is an extract of our training guide, right? And you can go to the LEARNserver and start doing this step by step. There are videos, there are documents. But what we do basically, right, is just to define first everything in 2D, right? The 3D element is way at the end. So what we define here is okay, many different ways, but one way that works for me is to define what we call help lines. So a coordinate system, right? If that inclined line, if it's going to rotate, right? For example, my pier will accommodate super elevation, right? And that will be that first three lines there are the center lines and vertical dimensions of the cap, then also the footing, right? And the connectivity that the cap will have with the columns, right? So I just do that. And then I start establishing the constraints, right? So this is kind of the outline of that. That's what we call it, help lines. And then I start defining the elements itself. So for example, this will be the 2D outline of the cap, and then also the 2D outline of the footing. As you can see, I'm not attaching any dimensions or, you know, perfectly drawing the dimensions because I'm going to adjust this with variables. Then the next step is to start constraining this. And then again, we have different constraints, right? So for example, I'm saying here that this coordinate system, let's call it like that, is fixed, so it's not going to move. And this is going to be the placement of the working point, somebody call it like that too, of when I place my abutment. And these two lines will remain perpendicular no matter what, right? So it's just, again, defining kind of a coordinate system. Done. And the same with my help lines, you know, they will remain connected and perpendicular here. And then this point also will be fixed. And then the perpendicularity on that IRS2. So I just defined it. Now, what else did I do? I said that, I mean, I didn't do the whole thing here, is on my cap, this line will always be parallel to this line. And this line to this line, and so on and so forth. Right? So when it behaves, they will constraining these elements. Again, I cannot tell you which one to use exactly. That all depends on the behavior of your element. But just to give you an idea, that's what it means. Right? So keep going with the constraining part. Right? That this element will remain also parallel to the coordinate system here. And then I can start assigning variables. So you can create these blank variables and then assign it to the options, right? For example, dimension the angle. Oh, but it's not I'm going to assign a name, right? And this will remain coincident on that point. So the angle will be measured like that, right? And then this line will be parallel with this line. So when they rotate, you see, it just goes together.
Getting them at 1 o'clock and everything.
So this is how this is all done,
yeah.
Right? And then remain parallel as well with the other element. So this is what you need to behave on that constraints. Then equal distance. Okay, so that line, again, it's symmetrical, right? So, and then when I dimension this, I can just start applying all these variables that I defined to the right, that at this point, they're only text. But then when I dimension, right, I can just assign that proper variable. So distance here too, right? The same for that. So it's equal distance, so it's symmetrical. Right, and then I can keep defining all these properties on the dimensions as well. So again, these are the ones that are going to be exposed. So for example, that dimension is what? Oh, that dimension will be the length of my cap. Right? So now if I define the constraints properly, when I change that dimensions, right, my whole, in this case, 2D pier will react and move accordingly. Well, if it doesn't, well, you know that your constraints were wrong. Right? So this is one way to test. And again, I suggest you to test step by step rather than finishing the whole thing and test it afterwards. Right? So element by element, you can start dimensioning all of that. right? So right here, so that dimension will be the depth of the base, for example. So, and again, you don't need to make everything parametric. If you know that you have hard-coded dimensions, well, just draw it properly and don't touch it, right? So it's only apply on the dimensions that you want to modify. And then, of course, the constraints have to be accordingly defined as well. Then after that, then we can say, okay, the 2D elements are done, then they behave properly. So now let's give it some depth, right? And then this is just no parametric that much, it's just solid by extrusion, right? So we just say extruded at a certain distance, and that's the variable, right? Remember, I mentioned the center lines. So basically, I just say that is half of the cap, half of the width of the footing, and the columns too, right? Define that. So again, it's solid by extrusion. Right? Now, since it's the center line, I need to sort of clip the extra part of the column that is going into the cap. So I can clip it, and what I'm going to use is a command called unite. So I will just select the elements and unite it with the solid that represents the cap, right? So where's the command? So that's it, unite. Accept it. That's it. So now I have my pier, right? And it's behaving that parametrically. Still, I can apply some 3D commands there, constraints. For example, because I have defined, I want the radius of the column to be parametric as well. So I can define that constraint too. And that line will be coincident with the center line of the cap as well, right? So I just have to define that. I haven't done it in 2D, so I do it in 3D now when I have also the dimensions of the radius. So basically, I'm done with my design. So now this is a DGN file, but we place it as a cell. So a trick will be to just rename this, because now every cell is basically a DGN now. Rename it as cell, and I can open it either on OBM or MicroStation, doesn't matter, right, at this time. So on that now, what I'm going to do is just change the name of the model to the name of the cell that I want to name it, right? And also make sure that the cell type, that is important, that is a parametric cell. So now this file needs to go into OBM. Let's open it, because the last step is to say what element is what. So that cylinders are columns, that prisms are a cap or are a footing. So we need to add what is called the variable tags. So I open it in OBM. And do what is called the assign tags and variable mapping. So it's just a matter of selecting the solid and say, oh, this is the cap, right? And the variable mapping is that the one variable called length of cap is just cap length. So it knows that, and the angle too, it recognizes. So when I modify the angle of the cap in OBM, the cell will map this variable, connect it, and modify it. Right? So the next step now, after that, it's ready, right? But it's not a parametric cell yet, because what you need to do, I think it's actually then later after that, we just need to, after adjust the properties and the cell, we just have to place it into the proper folder, and in the functional components folder in OBM, and be able to place it. Right? Now, what is the challenge in here, right? For example, these functional components, before attempting to start creating the models, right? Just study these cases, study what you're going to have, right? This is an example on when we started studying some of the DOT abutments, right? In which we say how many abundance with how many parametric models, how many functional components. And we ended up with 7 different cases, right? Because depending on the type of abutment, the type of beams that they were doing, the type of corner blocks or hinges and the behavior. So we ended up with 6 or 7 functional components to be addressed. So 7 different cells. And the challenge as well is if you're planning to attempt these, right, and you wanted to make it as general as possible, is study the behavior of that. Sometimes we used to do or to draft these in 2D, well, we just adjust it in 2D. But then when you're doing functional components, remember, you need to understand the behavior. What happened if the wing wall is at 15 degrees? What happened if the wing wall is at 30 degrees? That everything behaves the same. What are the distance? So all of that needs to be studied before attempting the parametric cell, because this is not something that you can come back and do it in the, fix it in the middle, right? So all these cases need to be studied, documented, then start doing the parametric cell, right? Because then you will save yourself a lot of headaches trying to accommodate a specific case. So this is, okay, and then the formulas that you need to apply, because on the variables you can apply formulas between variables, simple ones, but still formulas that you need to fully understand for every single case, right? And then achieve wing walls like this, for example, or excuse me, abutments like this one, right? In which for the end user to draw these in just regular MicroStation, 3D could be quite challenging. But here, if you just apply the proper dimensions or variables and then the behavior of these blocks, so then it could be just a matter for the end user to change variables, and the 3D will be drafted and accommodated accordingly. But then to develop these, you need to know, of course, how, especially in this case, how these corners behave. That is, again, what we find out in the DOTs that we're working with is that is the challenging part, understanding the behavior in, let's call it computational way, rather than a drafting way on how this behaves. After that, I mean, it could be simple, it could be as complex as you want it to be, right? Because you can achieve all of that with piers on abutments, right? Or not even that, you can also do, somebody asked before, what about if we do cable stays? Well, the pylons, they are not regular columns, right? So then you can also achieve it with functional components. And as I said, at the end of the day, you will create a library of abutments, a library of piers. So that library, when you're going to access and place it, it will just be a matter of saying, I'm going to place a custom pier, for example, and then it will be custom or a custom abutment. So for the end user, it will be selecting a template that at this time he knows that since he has variables, that it's a parametric cell, it's not just a static one, and it will be placed as part of the bridge, right? So as I said, for the end user, there's no difference. It's like placing any other pier. Right? However, it's known that the type is parametric, right? So he can place another one too, but now it comes as the default dimensions that you establish when you create the cell. Now, if you need to modify it, then that's where we go into the next step, in which we say, well, this is placed, what about changing dimensions, right? But then also I apply the tags. Remember this, it's the cell will have the tag. So if I go, my quantities are computed because I assigned the proper tags to it, right? And we don't, we just sell parametric cell, right? But if I apply the proper tags, the quantities should be already there. So basically computing the solid model that you assign. Now to modify properties, so I can just go select the element and go to my element properties. This is how we place it. So we can change these, Remember the map variable? Can do that. But these are the properties of the pier itself, how it's placed, the angle, right? Certain dimensions. But then what about if we want to modify the actual dimension of the column, the actual dimension of the footing? So what we need to access then is the properties of the element itself. Not just that, but the actual properties of the element itself. Not the peer properties, but the element again. It's a custom element, and then that is when it shows me all the variables that my administrator, for example, defined. Right? So I can start changing dimensions right there, and my peer will just change automatically. Right? So as you can see, the feedback is immediate on the dimensions that I need. Right? So define pile columns also. Right? I can do it too, and define them. Right? So every case could be different, and then it will be able to do it. So this is how you access that information. Right? So basically everything could be a parametric cell. Right? And then when we use this, there are certain limitations that you really need to be aware of. Right? We know that sometimes there are very custom structures that, it cannot be handled. Maybe it could be way too complicated, or maybe, after studying these abutment cases, as I show you before here, we don't end up with 4 or 5 cases. We ended up with 20 sometimes, or even more. Right? So there is not a generic solution that will solve all your problems. Right? So I would say that's the recommendations here. Create a parametric cell based on the specifications and try to pinpoint not a generic solution, but maybe a custom solution, but dedicated one as well. Right? Well, our excavation tools don't work with that yet, and the step cap options on bearings is not implemented yet. But my point is, what about if we don't have? We ended up with so many cases of parametric cells, right, that it could be kind of impractical. Why we ended up with that many cases? Because sometimes we need to do if conditions, right? If these cannot be used, I use this. If the number of if the super elevation is that, we need to resort to a different type of bearing, right? The number of piles, it needs to be adjusted according to the weak walls. I mean, a lot of conditions could happen, right? So again, we cannot develop that many parametric cells because, as I said, it will be kind of impractical to manage. So we encounter these problems as well when we are developing some of the abutments for many DOTs. So in Bentley, we resort to say, let's check on this tool that we have in our programming briefcase, that it was generative components, right? So generative components, basically, it's visual programming that we are allowed to use. Again, this is not a new tool. Open Buildings in Bentley was using this for quite some time, but after that, nobody else was using it. So we decided, what happened if we start experimenting this and do it in Bridge, right? So it's kind of a visual programming. You can do scripts. There are many different levels in which you can use this engine called, not generative components, actually the engine internally is called computational design. So, and again, there are many different levels in which you will define nodes and connections to it. Each node, this is a library available of nodes, behave on certain geometry. Like, for example, you want to place a line. There is a node that places a line. And then you select within that node place line, you select how you want to place it. Place by 2 points, place by distance and angle, right? So many options to place one line. So the node is something that we provide, Bentley provides to you. So you just selected how to connect that, right? And the connectivity is that wires, in which after you place the line, you will say, okay, I want to place the line and connect it to another line. So that will be the output connecting to another, and so on and so forth. Okay, but the key is that, as I said, it has many different levels. So it's not just for drafting, right? So you can just define the node, right? But also you can do some scripting there, internal, right? But then if you want to be some more advanced stuff, it has no limits. That's what the beauty of this. You can also incorporate actual code, I mean, like C#, into the node itself that you create and make it behave as you wish, right? How can we use, and then again in Bentley when we started using this in Bridge, in OpenBridge, right? So what about if we try to do this in 2D, right? So again, this could be a parametric cell, but then we say, let's try to recreate the same in GC and see how if we can make it behave. So again, this is how more or less it works. I can give you this. So you have to start with a base coordinate node, and then after that, I just place that this is where we're starting. These are the properties of that node, asking you, well, you're going to place a coordinate from where, right? At what point? So every node has an input, and every node will generate an output, right? So, for example, placing a point. How do you want to place a point? From the coordinate system, right? I'm going to place it by XY coordinates, right? So, and this is how we connect. So you place lines and make decisions based on that. So again, there is also, now we just put it in our LEARNserver, some presentations on generative components. Again, this tool has been used for a long time. So there is also, if you search on generative components on the LEARNserver, there is some material to it. We're planning also a training class on generative component, but just for bridge elements. So keep in touch on that. We're going to be announcing this kind of soon because, well, I will tell you later. But this is how this works, right? So now, and then we can use it to generate. You know, these wires, it may seem complicated, but it has certain logic to it. It's not that much. And then you can just, you know, place, for example, and then one of the usage of that was to be, you know, what about if we want to try different retaining walls heights? Then the same, we define variables, and it just adjusts it automatically, depending on the controls. We call it controls, but these are the variables that I set up to adjust for this. Right? But at this time, when we were testing this, these graphics that you see were not, let's call it microstation elements. The generative components was a separate engine. You're all user of OpenBridge, we used to have an icon called Generative Components, in which you have to actually get in, launch the engine, computational design through that. So that's what we have, right? But now what we did on this later release, that by the way, it's the 2022 release 1, is out, has been released, has been activated, ready for download, actually today in the morning. So you can start checking these new enhancements that we have. Again, announcing two in the YouTube page on our OpenBridge channel. There is the whole presentation of what's new in OpenBridge, the same as we did 2 days ago on this conference, right? So what we did on that was the ability to run, actually, and that is a big improvement on our side, to run the computational design engine inside OBM. So we don't need to an extra icon or just exit out of OBM and do it. So we can run it all inside, right? And the idea is to the administrator or the GC person to create these abutments, to create these piers and make it available to you end user as a library. So he will create what is called a GCP file. So that is the node, specially created node that will place your abutment 1 or abutment 2, and it will be another node inside the node types available in the GC engine. So you just need to do that, and it will be present every time you launch it, right? And then you decide that, hey, abutment 1 node is the one that I'm going to use in my OBM. Saying that, which some default dimensions there, that the coordinate system that the GC component is created is the same as we're going to use for placement in OBM. And some other variables that we may need to map, like for example, the skew angle in the GC element is the placement angle in OpenBridge. And if we don't need to define any extra ones, that should be okay. The only one extra is that Z translation, that it computes the vertical offset. So it's going to read the deck, the beams, and then that's going to place the abutment there at that dimension. And then for the end user, it will be just place a custom pier, just to make it general, and then you just select the template that you want to use. Let's call it template, but really what it is a GC node. So it tells you that it's a GC node. Select the support line and place it. Right? So it will be adjusted to that. Let's wait until it computes everything. And that's it. So that is the abutment being placed. Right? And then we can continue placing this in the other one, right? Adjust the placement angle, for example, right? Nothing else. You don't need to worry about the vertical offset or anything like that. It's just select the element again and place it. So now, after the fact, I mean, this will come as the dimensions are stored in default when I created the GC, right? So then we need to modify it according to our needs, right? Or maybe the placement angle is wrong, or the wing walls, the heights are different than what I need, the number of piles. So it all depends how I get you customize this, right? So it's placed, but again, maybe it's not the dimensions exactly what I need. So I need to go and modify it. So let's switch this to transparent to see what it has done. Right. So now to modify the dimensions of these, right? Again, it's not, as I said, exactly what I need. Maybe the wing wall is longer, right? So then I should go and switch to my workflow, to the computational design workflow. Right. So it will show the nodes that have been placed, Pier 1 and Pier 2. This is the one that I'm going to edit. And this node, if you double click it, it has properties. Right, so these properties are actually the variables that are defined by the person that created this GC. Right, so, and then again, these variables should mean something to the one that created it, right? And so then you can start changing dimensions there, and the abutment in this case will behave immediately. There is no need to rerun. There is no need to replace it. Right? That was the big improvement as well as we did. So you change dimensions, you have immediate feedback as soon as you hit enter on how this actually works. Right? So, and that will be the GC placement there. Now, how many nodes you can have? As the idea is to create a library of this, being able to place it. Certain limitations at this time. Remember, this is a tech preview on our site. Is we are not all of these are solid elements. So, but then later we are going to include item types, better quantities, right? So include some decorators too to read all that information. Right? So I just wanted to highlight these are the options in which we place these GC elements there. Right here, for example, oh, I made a mistake on selecting the angle, so we can also go back to that properties or place it, or just go back to where I place my pier and select the placement. Right. So as I said, there are extensive references through not only OpenBridge but also through the Generative Components sites in general. So I listed some of them, but again, some of them applies to building as well, right? But the commands are the same. And we're going to be offering later a training class on GC because there are certain elements that you need it as well. They need to be recognized, for example, as civil elements. They are not there quite there yet on that part. So it's a lot of it's room for improvement, not only to use it in Bridge, but also use it on open roads as well.